Let's start.
So good evening to all the attendees, and thank you all for joining this eminent foreign lecture series today. Along with me on screen, you can see Professor Dr. Vishwajay Chatterjee, Vice Chancellor of University of Engineering Management, Jaipur, and Professor Tom Baxter, who is guest and keynote speaker for today. Thanks to our Vice Chancellor, sir, for giving me this opportunity to host the event. And I welcome you, Professor Tom, on behalf of the entire IEM UEM group, and wish that today is going to be another big learning day for all the attendees. So before we start the session, I'll just take a minute to introduce Professor Tom. Tom Baxter graduated from Strathclyde University in 1975 with B.Sc in Chemical Engineering First Class Honours, and he is also a fellow of IChemE. He started his career with ICI Petrochemicals, moved to fine chemicals with Swiss company Ciba-Geigy, before taking a position as a process engineer in 1980 with BNOC, that is British National Oil Corporation. So he worked as operations engineer, development engineer, and research manager at BP Talisman. And since 1991, he worked with Altra Consultants as technical manager and accepted a position as technical director with Genesis in 1998 and became the Aberdeen Business Unit Director in 2005. He returned to his role as technical director on 2010 together with a position as senior fellow at Aberdeen University, where he also helped them to establish the Department of Chemical Engineering. Since 2003, he has been a visiting professor of chemical engineering at Strathclyde University, and he is currently a chemical engineering consultant providing greenhouse gas reduction expertise. So today, Professor Tom will be talking whether hydrogen as a wonder fuel is being oversold, and if we do have an alternate to that, and if yes, if we have an alternate, then what is the effect on energy efficiency part? So that's all from me. Professor Tom, it's over to you.
Well, thank you very much, and thank you for giving me this opportunity. The topic will be energy efficient carbon capture and storage. So what I'll do now is I will turn off my camera and we can get started. I suggest you let me finish the presentation, and then we'll have a question and answer session following that. So we can see the topic. So the context here is to the left, we have a gas supply. Typically in the UK, that would either be from offshore gas fields or perhaps imported LNG. And the gas is taken to a power station, a combined cycle station, where electricity is generated and the flue gases are treated for carbon emissions. The carbon's captured, compressed, and stored in a geological trap. Just a little reminder of a combined cycle gas turbine. So we have the coupled gas turbine, we have the air compressor. So we ingest air, compress air to combustion temperature, inject fuel. We get a rapid expansion of the combusted gases, and the energy in the expansion is taken out through a turbine onto an alternator, and here we generate electricity. Electricity generation is supplemented by a heat recovery steam generation system, where the heat in the flue gas is used to generate steam to drive a steam turbine coupled to an alternator to give us supplementary electricity. Now, if we deploy carbon capture and storage on a combined cycle gas turbine, we introduce a parasitic load. The parasitic load results from, we will take steam that could be used for electricity now to help in the recovery process of the carbon dioxide, and we'll use some of the electricity to power the gas compressors, the CO2 compressors, and the ancillary equipment. So these two red sources reduce the power output from the power plant, reducing its efficiency. So it's an unwelcome introduction that we have for carbon capture. And clearly, the lower we can make that parasitic load, the smaller we can make it, the more efficient we can make it, the better the efficiency of the combined cycle gas turbine generation station will be. So just a little bit of background, combined cycle. In the UK, this is Wales, yeah, so it's to the west of England. And down on the south corner here, a little red dot, is the Baglan Bay power station. And the Baglan Bay has frame 7s and frame 9s, General Electric machines. And as you can see, the thermal efficiency is around between 55 and 60%. 60% is actually a very good thermal efficiency for a power station. Now, this is Petronova, one of the built carbon capture plants on a power station. It's actually on a coal-fired power station, but the function of the carbon capture plant is exactly the same as it would be on a gas-powered station. So Petronova is near Houston, and you can see the flue gases. This is the amine absorber taking out the flue gases, the amine regenerator releasing the CO2. We have the CO2 compressors, and somewhere there'll be an exit route, an exit pipeline for the CO2. In this particular application, the CO2 isn't used in storage, it's used to enhance oil recovery. So there's a commercial value in the carbon dioxide. The injection of carbon dioxide improves the oil recovery from nearby oil fields. So let's have a further look at the system here. So the amine unit. Now we've got here the amine reaction. So we have amine is an NH2 radical, NH2, that will react with CO2 and bind the CO2 to it. So let's follow the process flow diagram. We're coming in from the power station, the flue gases, which will quench, will cool. Now we have to increase the pressure, and we increase the pressure to allow the gases to overcome the pressure drop in the contact column, the amine absorber. So the flue gases with carbon dioxide in them flow upwards. They are met with counterflowing, downflowing amine. It's called lean amine because it's very little carbon dioxide in it. And the lean amine captures the CO2, and we have rich amine leaving the bottom of the column. So that's amine with the CO2 chemically bound to it. We then take the rich amine over to a regeneration column. So if we follow through, we've got some heat recovery here where the rich amine is heated, and then the heat is further supplemented by a reboiler, and that drives off CO2 and water and some amine, which we condense, reflux, and we have a typical distillation process going on here, a stripping process, where the CO2 is stripped out, the amine and water come to the bottom, and the CO2 at the top goes forward to compression. Now we've stripped the CO2 out, we've got lean amine, and this lean amine is taken back, it's hot. So we use the hot lean amine to heat the rich amine to take a load off the reboiler. We're using heat integration here as a form of energy efficiency. We then cool the amine to the contact at temperature, and the process repeats itself. So it's continuously removing CO2. And the big energy users are the amine reboiler, the flue gas cooler, and these pumps are fairly large too. But the blower and the boiler are the biggest users. We then take the CO2 forward, and we're now going to take that to a sequestration site at the top. And generally that's done with an integrally geared compressor. And what I've shown you here is 5 stages. So from the Amine stripper, this will be around atmospheric pressure, can cool, compress, cool, knock out any liquids, compress again, so second stage compression. Here we have a dehydrator, and we will remove water. And generally you will remove water to prevent corrosion. CO2 and water is a very corrosive mixture, so if you've no water, you tend to have you'll have no corrosion. So we'll also have a look at the dehydrator. But before that, we continue. So 1, 2, 3, 4 stages of compression. At this point, generally you're above 100 bar, and the CO2 is now acting more like a liquid. And the last stage is often get the characteristics of a pump. The CO2 is beginning to become more incompressible than the low pressure compressible CO2. Gas dehydration, what I've shown here is a molecular sieve unit. So at the top we have the wet CO2, so that's CO2 that's been saturated with water, and we want to remove that water. So we have a 2-bed process or a multi-bed process here. The one I've shown is a simple 2-bed one. One bed is on duty, one bed is regenerating. So the valves are aligned such that the wet CO2 comes in, this is open, this is closed, and the wet CO2 flows through this desiccant material. It's a metal aluminosilicate. So think on that, just general silicate, that will absorb water. And so the process of absorption is a molecule adsorbing to a solid surface, which is different from absorption into a liquid. But in time, this bed will become saturated with water and eventually will become ineffective. So before that happens, we have to get this bed offline and drying. So whilst this is adsorbing, this bed, this parallel bed, is being regenerated. And what's happening here is around 10 to 15% of the gas is heated, maybe to around 260 centigrade. It's then routed along here and then up. And the hot gases release the water from the molecular sieve solid adsorbent. And then the hot gases with water are taken out, cooled, and the water is taken off, the condensed water. This gas, the regeneration gas, has residual water, saturated water. So this comes along and meets the gas here being dried. So when this is ready to be regenerated, the valves switch over. This becomes a drying bed, and this becomes a regenerating bed, and that will cycle typically on it around 8 hours. So let's do a simple heat and mass balance. Let's do a simple heat and mass balance, and I'll assume that we want 1 megawatt of electricity from a combined cycle gas turbine plant, and the thermal efficiency is 55%. And we'll also assume that the fuel gas we're using is methane, and methane has a calorific value of 50,000 kilojoules per kilogram. So if I do a simple analysis, so 1 megawatt at 55% thermal efficiency using methane results in 0.036 kilograms a second of methane requirement. So if you look at the combustion reaction, for every molecule of methane, I produce 1 molecule of CO2. So we know CO2 molecular weight 44. We know the molecular weight of methane, so we can estimate the amount of carbon dioxide that we're producing, which is 0.1 kilograms per second. Now the flue gas that I'm using, I'm assuming is a molecular weight close to air. It's got a molecular mass of CO2 of 8%. So knowing that CO2 is 0.1 kilogram per second and an 8 mole% concentration in the fuel gas, I can calculate the mass of flue gas is 0.8 kilograms per second. So the key numbers here, for every megawatt of power, I'm producing 0.1 kilograms a second of CO2 and 0.8 kilograms a second of flue gas is required as feedstock. So let's have a look at the blower. So that's the compressor, the axial blower compressor that provides an increase in pressure on the flue gas to allow it to overcome the pressure drop in the amine absorber. And typically that will have a discharge pressure of 1.3 bar and a suction close to 1 bar. So we actually have a huge volume at 1 bar atmospheric pressure of flue gas that we have to compress. Although it's to a small pressure, it still requires a lot of energy. And a simple polytropic calculation, as I've shown the equations here, yields 21 kilowatts for that blower. Now remember, we're producing 1,000 kilowatts of electricity. So 21 is now a parasitic load. That's 21 kilowatts that we can now produce as sales electricity. Now, what I've done here is for a typical amine reboiler to regenerate the amine to get the CO2 out of it, literature shows that it's around 4 megajoules per kilogram of CO2 of heat requirement. Now, for the numbers that I use, bottom left, I've given a source. So I'll provide a PDF of this presentation, which will hopefully be made available to you all. And if you're interested, you can track down my data sources. So 4 megajoules per kilogram of CO2, and I've got 0.1 kilograms a second of CO2. That means the thermal duty on the reboiler is 400 kilowatts. Yeah. Now that's 400 kilowatts I have to supply as steam. Yeah. And that's 400 kilowatts thermal that now can't be used to generate electricity. So what I've done here is I've used, as you can see, I've got a reboiler that's around 400 kilowatts, and I'm looking at how much steam that uses, and I get a quantity of steam, yeah, of 36 kilogram moles per hour. So that's steam that, as I said, we can't use for electricity. I now take that steam to a steam turbine to calculate how much electricity I could get, and I calculate 29 kilowatts. So there's another parasitic load, 29 kilowatts of lost thermal energy that could be used to generate electricity. Now if I move to the CO2 compressor, and I've simply shown this on a Mollier chart. So pressure on the x-axis, enthalpy on the y. So we've got our phase envelope. So all liquid, a mixture of liquid CO2 and gaseous CO2, and then all gaseous CO2 this side, and above the critical point, we're in the supercritical area. Yeah. So 5 stages of compression would be 1, cool, 2, cool, 3, cool, 4, cool, and then 5. And this is the one that says more behaving like a pump. Yeah. And we're getting up to around 120 bar here. So if I calculate the compression power here, I get 40 kilowatts. The molecular sieve, I assume 15% of the flow has to be heated to 275 degrees centigrade. So that's 5 kilowatts, another parasitic load. And then we have pumps and all the other utilities that we need, the balance of the plant, I've assumed it takes another 5% of power. Yeah, and that then adds up to the blower, the amine reboiler, dehydration, compression utilities, 100 kilowatts. So remember, we were generating 1,000. Well, we now have a parasitic load of 10%. That's for combined cycle. That would be as high as 15% if it was an open cycle gas turbine. And if it was coal-fired, that would be 20% parasitic load, approximately. And again, my references are down here, which confirms this 10% number for a combined cycle gas turbine. So what we want to do now is make this process energy efficient. So basically, I want to reduce these numbers. So let's consider how that might be done. Before doing that, one aspect as well is we have lost 10% of our energy as a parasitic load. To recover that 10% of energy means that the supplier of the gas has to work 10% harder, producing 10% more gas to give us 1,000 kilowatts, 1 megawatt. So that will result in more CO2, more SOx, more NOx, and more particulates from the supplying gas companies. And that's something people don't often consider, is there's a knock-on effect because of the parasitic load that means we have to produce more gas. And in doing so, that produces more CO2 and other harmful emissions. So I said, let's look at reducing our energy, the base case energy. So firstly, I'm looking at the blower. Yeah. Now the blower's there to overcome the pressure drop in the amine absorption unit. And the pressure drop is induced basically by the packing that's in there. So we have gas flowing through here with the CO2 in it, and counterflowing would be the amine, so structured packing. Now I'm using Sulzer packing here, and Sulzer and some others have developed packing with very low pressure drops. So here's the pressure drop, delta P per meter, millibar per meter. And these are more conventional packings. So the trade names of the packing, yeah, with different loadings, yeah. Melipack CC and CC's carbon capture is much lower in terms of its pressure drop. So if I have low pressure drop packing, it means the blower would require less energy. So I'm into the blower now, and what I'm looking at is the polytropic head. So P2 upon P1 is discharge to suction pressure. I can lower that, yeah. Another thing I can do is reduce the temperature further. So that will reduce the polytropic head, which in turn will reduce the power. Yeah, so power is mass rate times polytropic head divided by the efficiency. And of course, the more efficient I can make the blower in terms of its hydraulic efficiency or overall efficiency, the less energy I will use. So I've dropped the discharge from 130 as the base case down to 120 kilopascals, 1.2 bar, and I get a big saving. Remember that was 21, it's dropped to 14. If I cool from further, I had in the base case 30 down to 25, I can get a little saving. And if I design for a high efficiency compressor, I get another saving, 4%. But the big saving here is the low pressure drop packing. Another option I've got is a technique called split flow. Split flow, yeah. So what we've got here is the same flow sheet as I described earlier. So the flue gas coming in, flue gas blower, the flue gas with CO2 in it moving upwards, amine moving down. Now, the lean amine here really has to have very little carbon dioxide in it to catch the bulk or the last of the carbon dioxide. However, partway up the column, the amine doesn't have to be as lean as it does at the top. So what we could do is take partially conditioned amine, and I've called it semi-lean amine, from the middle of the regenerator and put that into the middle of the contactor. And that actually reduces the load on the reboiler. If you can recall, that was 4. It's down now to 3.7. So almost a 10% saving through a split flow amine package. And that's of interest. But of course, I'm adding more cost, more complexity with this system than the previous base case system. There are proprietary solvents that are being have been developed and are being developed, and one is Mitsubishi. The solvent is proprietary, so it's known only to the vendor, and here they are providing a solvent where they're claiming 2.5 megajoules of reboiler energy per kilogram of CO2. And here in the UK, Sea Capture, they're working with Drax, is one of the major power station companies in Britain, to develop a solvent with an energy value which is around half or less of the 4 megajoules per kilogram CO2 for a conventional amine unit. So some significant savings possible here. For the molecular sieves, we could look at some heat integration. So when this bed has been regenerated and there's some hot gas coming over, rather than just cool that, we could perhaps use some of this hot gas to preheat to allow us to reduce the load on the regenerator. So there's another energy efficient option that we may deploy. I mentioned the integrally geared pumps. Yeah, so we've got generally mixed flow impellers driven from overhung cogs that allow us to run each stage at a different speed. Now that allows us to try and get to the sweet spot in every speed. So we've got specific speed on the x-axis and the efficiency here. So we can try to get our best efficiency from the geared compressor. Now, what causes thermodynamic or fluid losses in a compressor is shown here. So here we have a mixed flow impeller. So the CO2 is coming in here. Yeah, the impeller's turning, and the CO2 is getting into the diffuser, and we're converting the kinetic energy to pressure energy. Now, where we have losses, one is this friction, and the arrow is pointing to this space here. So we have a turning impeller against a static casing. Now, what you generate here are secondary vortexes that induce a drag on the impeller, so it induces inefficiencies. Surface roughness, so the smoother the surfaces are, the less frictional pressure drop we have. Leakage, we have high pressure CO2 here, low pressure CO2 on the suction side. So we've got a pressure force wanting to push the CO2 back to the suction side. And if we've got clearances between the static faces and the rotating faces, we can recycle high pressure CO2 back to the suction. Leakages, which result in inefficiencies. And anywhere we have a flow direction change, where we have a momentum change, or we induce eddies, will be another place where we will suffer inefficiencies. And it's interesting to see how compressor design has improved, because we can design and manufacture with much greater tolerances now. And this is from Sulzer, and they were claiming they could design a compressor at 88% efficient, yeah, which is that's pretty well best in class. But this is going to cost you a lot of money, yeah, compared to maybe a 75% compressor. And we have this cost efficiency trade-off. So let's have a look at the CO2 compressors, yeah. So the duty is 1 bar to 120 bar after a cool of 30 degrees C, and the pressure drop between stages from discharge of one compressor to the suction with the other I've taken as 1 bar, and the base polytropic efficiency 75%, and that gave us a base case compression load of 40 kilowatts. I'm now going to have a look here again. If I can reduce the differential pressure in between stages down to half a bar, I can get a 6% saving. That's pressure that the compressor doesn't have to recover. Every time of a pressure drop, a compressor has to recover that lost pressure. If I drop the discharge temperature down to 25, so that's the feed temperature for the next compressor, I get a 3% saving. If I move the efficiency up to 80%, 6% saving. And if I can lift the suction pressure, which is the regenerator pressure, by 2.5 bar, I can get 11% saving, because that's a large reduction in overall compression ratio. Before it was 120 to 1, now it's 120 to 2.5. Other places I might look for efficiency is very high efficiency motors, the use of dry gas seals, and maybe the use of magnetic bearings instead of conventional roller bearings. So if I combine that together, I can put a view of an energy efficient carbon capture plant. So this was our base case at 100 kilowatts, so 10%. I can reduce that by 25%, deploying some of the techniques that I've shown you, and that will increase the power station efficiency from 49.5 to 50.9, a 1.5% increase in overall thermal efficiency, which is quite significant for a power station. So the drive for efficient carbon capture plant is quite clear. I'll introduce another thought to you now, and this is a device. It was part funded by the US Department of Energy, and it's called a Gen Compressor. And this works on the principle similar to a jet aircraft that is supersonic. And we have a casing, and in the casing, rotating is a kind of angled shape like this. And as it rotates, the CO2 is rammed into this gap here, where it reaches a speed of around Mach 2, and then expands out on the discharge side, and we recover that velocity as compression or pressure energy. Now, the claims, and it's been demonstrated that this machine can give you a 10-to-1 compression ratio. Now, that's very significant. So instead of having, remember, 1, 2, 3, 4, 5 conventional integrally geared, if we go for a 10-to-1 compression ratio, I've got 2 stages of this supersonic compressor. As well, very interesting is the fact that I now generate temperatures of around 250 degrees C. So I've got some high grade heat. Now I could take that heat, and what I've done here is, here's our 2 compressors. These are the Gen supercritical compressors, generating something like 250 centigrade. What I've done is I've taken that heat and generated steam on these 2. And I've looked at the amount of steam that I can generate, and it's about thermally 600 kilowatts, and that will reduce the load on the reboiler, the Amine reboiler, by about 0.6 millijoules per kilogram. So again, a very significant energy saving, where I'm integrating the heat of compression from the CO2 plant back to the reboiler on the CO2 capture plant. You won't be able to see this, but this is one of my models. Some of you guys might recognize this as Aspen HYSYS. One aspect, and I'll try and get a student working on it, is to overlay an optimizer, and we can try a multivariable optimizer to see if we can get any more energy saving. So a few more slides left. Obviously, carbon capture plant is going to cost money, yeah. And this is from the Global CCS Institute. These are their numbers. So for a natural gas combined cycle plant, the base case is $49 per megawatt hour. If we deploy carbon capture, it goes up to over 70. So it's a very significant cost increase by deploying carbon capture. In the UK, the largest scheme that was proposed was this is so you recognise the UK. This is where I live up here, and the gas plants are north of Aberdeen, where I live. And it was proposed a carbon capture plant would go on the power station adjacent to the gas plants. It's called the Peterhead Power Station. The gas would be captured, CO2 removed, and then taken to a platform, an offshore platform that had CO2 metallurgy in its construction, CO2 wells, and use that as a sink for the carbon. It was to be deployed in one train, one CGT train, the combined cycle train. So it was around 44 megawatts, sorry, 440 megawatts, 48% efficient. But we know power station CCS is very expensive, and there's no commercial driver. All CCS does is cost money. So maybe no surprise, the project was cancelled. This is the status of carbon capture plants worldwide. So we've got power generation, and the reds are in operation. And the one I want to draw your attention to, so is power generation gas, power generation coal, is Petronova. I mentioned that at the start, yeah. And we see that's purple. Operation suspended. So it was working, they've suspended it. And the reason they've suspended it is Petronova catches carbon to then be used to enhance oil recovery. Oil prices have dropped. They are recovering somewhat, but they've dropped to a point where it wasn't commercial to operate the carbon capture plant on the coal-fired power station. So the plant's been mothballed. But there were some worrying words here. There's a quote from one of the economists. Proponents of these projects are selling an unproven dream that in all likelihood will become a nightmare for unsuspecting investors. In the UK, Lord Oxford said CCS, there is no commercial incentive, and until there is no business case. And I noticed a DNV paper looking at carbon capture with hydrogen, and this quote here is, can you see it? The oil and gas industry, nearly 3/4 of respondents say that oil and gas companies will decarbonize only if it makes financial sense. And here's the outgoing OECD president saying, put a big fat price on carbon to make carbon capture commercially attractive. And I think this is my last slide. This was a proposed new gas power station for the UK. There was no carbon capture proposed for it. They had left space available and connections for a CCS plant. It actually caused an outcry. It was challenged by the environmental groups, but the challenge was overruled. Since then, actually, the operator, or the proposed operator, has now reversed plans and is no longer going ahead with the power station. So that's me covered the material that I want to cover. Hopefully you found it interesting, some useful information here. I've got a series of articles in the Chemical Engineer, many of them called Energy Saviours, and there's one on the parasitic load for carbon capture. You might want to have a look at that, or perhaps have a look at some of the other articles I've written on energy efficiency. So once again, thank you for your attention. I hope you understood the Scottish accent, and I'll hand back to the chair and see if there's any observations or questions.
Okay, so that was a really nice session, and I would request Professor Umesh Gurnani. So if you can kindly switch on your webcam also, Professor Gurnani, if possible. Are you there? Okay. So yeah, there are certain questions in the question panel. So if you can kindly go ahead with that, if you can kindly ask the questions. I think you are muted. Okay, you are not connected via phone, which means, okay. So just a minute. Okay. Yeah, you can kindly go ahead.
Okay, so we do have a few questions in the panel. Like one of the professors has asked that what is the average height of absorption tower for a carbon capture plant?
Oh, 40, 50 meters. Yeah. It'll have about maybe 30 trays. Yeah, 30 to 40 trays. Yeah, for 40 meters. Yeah.
Okay. Okay. So Professor Gurnani, that was really a wonderful session, and you may kindly, if there are other questions, you may kindly proceed.
Yes, we do have one more question, that what is an efficient way to cool or prevent the heating up of batteries in a confined space?
Oh, well, I wasn't talking about batteries. The honest answer is I don't know. I'm sorry. I don't know.
Okay. And so you gave an introduction about the ramjet, which is also being used in the ramjet engines. So what is the principle that actually applies in ramjet, which enhances the entire efficiency of the entire system, the entire process?
Well, there's no leading edges really to cause a lot of inefficiencies. The technology is quite proprietary, and the technology has been bought by Dresser Rand. Yeah. So all I can suggest is there's a reference on the slides. So the delegate that was asking that question maybe wants to track down those references. But they do claim efficiency. But you recall that one of the key benefits I saw was that we now were generating high-grade heat as opposed to the 5-stage compression. And that high-grade heat could be used on the Amine regenerator reboiler, which is one of the biggest parasitic loads.
Okay. So currently, sir, we don't have any other question apart from this.
Okay.
Yeah.
All right. Well, I once again thank you so much for giving me this opportunity. It's a topic I'm very passionate about. So hopefully it was of interest.
Yeah. Thanks a lot to Professor Tom for sparing your time and delivering such a wonderful lecture today. And it was a real honor for all of us to hear from you. And as I could understand the lecture, like you almost covered the areas where hydrogen has been of the most prominent use, and then starting from the basic gas turbine cycle, you moved on to the combined cycle with enhanced efficiency, and like moving the gas through the entire process from blower, amine, dehydration process, compression, and the other utilities. You also showed like how the entire efficiency in the power station declines, and like the small modifications in the process can enhance the efficiency of the system.
Professor Gunani, I believe there is one more question in the panel which you might have
Yes, sir.
missed. Like this question was from Professor Shomnath Hazra. He
Yeah,
is
yes, sir.
asking what is the efficiency level of HRSG turbine in general?
The combined, well, the best in the UK thermally is just on 60%. Yeah. I've seen anything from 45 to 60%. It depends on the system that you've designed. Yeah, but at 60%, you're almost on the limit of what you can possibly get. You're just about there. Yeah. So the next option to make it more efficient would be using network heat. So you use residual flue gases, say produce hot water that then goes for domestic heating, and that would overall increase the thermal efficiency.
Okay.
I hope that answers the question.
Okay, thank you, sir. Thank you. It was really a very enlightening session, and I thoroughly enjoyed it. And I'm sure all members, all attendees must have enjoyed it thoroughly. We are grateful to you for your time, and I'm sure that this is a start. And in future, if you decide on coming on India after this whole thing is over, we will always invite you to come to Jaipur, come to our campus, or come to Kolkata, come to our
Yeah.
campus. Thank you so much, sir. Thank you. It was a pleasure. It was thoroughly a pleasure.
Okay. Thank you all very much. Bye-bye.
Thank you. Thank you
Thank you,
so
sir.
much.
Thanks a lot,
Thank
sir.
you. Thanks a lot.